Hi, my name is Joanna Klicka, and today I'm going to be going through HW1 Part A. The first question of Part A says, a cylindrical tank with uniform cross-section of 1 meter squared has a drain hole at the bottom of size 0.2 meters squared. Water has been flowing in at 0.1 meter cubed per second for a long time, and the liquid level has reached a steady state. Suddenly, at t equals 0, the inlet flow is increased to 0.15 meters cubed per second. Derive the differential equation describing the height of liquid in the tank and simulate the response using Excel and Python. The first thing that we are going to do is draw out this scenario so that we have a more clear view of what's going on. So first, we have our tank with water in it at some height H. There's liquid flowing into the tank and water flowing out. In our problem, we were given some of the parameters. So the first is that the cross-sectional area is 1 meter squared, that the outlet size is 0.2 meters squared, our Q in naught, so our flow for a long time, is 0.1 meters cubed per second, and our new Q in is 0.15 meters cubed per second, and that's all. If we come back over here, you can see I have all that written out. And the question that we're being asked here is, how is the height changing? So the first thing that stands out here is that we have two unknowns. We don't know the height, and we don't know what this Q out is. And since we're looking for the height, we first need to find this Q out value. We know that our Q out is going to be the area of this outlet, A out, multiplied by the velocity of the water coming out. So we need to solve for this velocity since we already are given the parameter of the outlet size. To do this, we can use Bernoulli's equation. So this is our pressure energy, P1 minus P2 over density, plus our potential energy, so G times Z2 minus Z1. And we're going to say that Z1 is up here and Z2 is at the bottom of the tank, plus our kinetic energy, so V2 squared minus V1 squared over 2, all equal to 0. At this point, we are able to make some cancellations, so we can get rid of this whole term since our pressure at 0.1 and 0.2 is atmospheric. We can also cancel out our V1 since the velocity, or since the cross-sectional area of the whole tank is significantly larger than our area at the outlet. Next, we need to find that G is 9.8 meters per second squared. Since we're making this a positive value, this implies that the downward direction is positive. We're also implying that H is positive, which in this case is Z1 minus Z2. And as you'll notice here, we have Z2 minus Z1. And so we can just say that negative H is equal to Z2 minus Z1 and make a simple substitution. So if we were to rewrite this, we would get negative GH plus Z2 squared over 2 is equal to 0. And since we're looking for V2, we can just rearrange our variables and solve for that. What we end up with is that V2 is equal to the square root of 2GH. Now that we have that, we can take this V2 and substitute into our Q out. equation. So now we have Q out is equal to A out times the square root of 2GH. Next, we're going to evaluate the volume of the water in the tank. So this is V is equal to the cross-sectional area times the height of the liquid. Then we're going to convert this into a differential equation since the volume of water in the tank is changing with time. So we end up with dACH over dt. And this is going to be equal to Q in minus Q out, since this is liquid being added to the system and liquid being removed from the system. At this point, we can pull out this AC since we know the cross-sectional area of the tank is going to be constant. So now we have AC is equal to dH dt times dH dt. dH dt is equal to Q in minus Q out. To isolate dH dt, we can divide both sides by AC. dH dt is equal to 1 over AC times Q in minus Q out. And finally, we can substitute this here in at Q out. dH dt 1 AC times Q in minus A out times the square root of 2H, which gives us our overall differential equation of a change in height. Oops. Oh, with time. Now that we have our differential equation, we can use Excel to solve using Euler's method. Excel, hold up. Workbook, and here we can enter our parameters. AC is equal to 1 meter squared. Outlet area is 0.2 meters squared. Our Q in naught is 0.1 meters cubed per second. Our Q in is 0.15 meters cubed per second. And then we have G equal to 0.9 meters per second squared. Now, to actually solve this differential equation, since it's an initial value problem, we need to have an initial value of H. So we go back maybe over here. We can solve this differential equation for when t is equal to 0. That eliminates these values here. So we can set this equal to Q in is equal to out times the square root 2G times H naught, the 1/2. This is also the Q in naught since this is at time equals 0. Now we can isolate H naught, which will give us Q in naught over H out times the square root of 2G H naught and the whole thing squared. We can go over and enter this into Excel. H naught to Q in naught divided by A out times the square root of 2 times G all squared. Q in naught divided by A out times square root 2 times G there we go. And that is in meters. I'm going to insert a counter for our steps. Go to series, columns, say 10,000. I'm going to make a column for our time, our height, and our change height. Okay. Next, we need to go back and evaluate our differential equation again, and we're going to rewrite it in a new form. We're going to say delta H is equal to Q in minus A out times 2 square root of 2 times GH all over AC times delta T. This will allow us to actually solve for what is changing in height. We can simulate what would happen if we increased our flow in. So for our delta T, we can just pick whatever we want. So we're going to pick a pretty small value, that's in seconds. And our time here is going to be our step times this T. Double click down. Our initial height is what we solved for, so that's here. And we also solved for that delta H. Just type that in here. And we have our Q in minus A out times the square root of 2 times G times our height multiplied by our delta T and divided by A C. And then our new height each time is going to be height, previous height plus our delta H. Double click that all the way down. Double click this all the way down as well. And now we are able to plot this, so we can select these two, insert on our scatter plot, and we can see how the height of liquid changed within the tank. Now this method is not perfect since it is subject to round off errors, so next we are going to do this same thing in Python with a different method. Now we are ready to solve this differential equation in Python. So I'm going to start by importing the libraries that we'll need. I'm going to import numpy as np from scipy.integrate, import solve underscore ivp, and from plotly dot subplot import make underscore subplots. Now I'm going to enter all of our parameters. AC is equal to 1 squared. A out is equal to 0.2 meters squared. And we have our Q in naught is equal to 0.1 meters cubed per second. We have G is equal to 9.8 1 meters per second squared. And this time we need T end and end time. And we're just going to pick 10 seconds. Just like with Excel, we need an initial value, an initial height to solve our initial value problem. We're going to use the same exact equation that we used before. So we have H naught is equal to Q in divided by out times NP dot square root times 2 times G all squared. And now we are going to make a function to solve our differential equation. So we're going to define it to h to t, and then we're going to put an independent variable time, dependent variable h. We're going to do q in is equal to q in naught times 1.5 to show that 50% increase. And then we're going to return our differential equation, which is what we solved for way back at the beginning. So this is our Q in minus A out times NP dot square root times 2 times G times H, all divided by AC. Now that we have that, we can say result is equal to solve underscore IVP. Put in our function dHdt, and we put in our time. So we have 0 times 0 to our Tn that we already defined. We have our initial value, which is H naught. We have our method, which is going to be the do. We're going to say dense underscore output equal to true. Must be. Just spell it wrong. There we go. And now we're ready to plot, so we can do our x-axis as t plot is equal to p dot ln space 0 to t end 2.1. Then we have our y-axis, which is h plot, which is going to be result dot solve plot. Okay, now we can do here is equal to make underscore subplots. And we want to make it a scatter plot. Scatter. X equal to our t plot and y is equal to h plot. Pretty sure this is add underscore scatter. There we go. So h plot. And then we're going to update the layout so that it looks nice. We're ready with is equal to 600 and our height is 100. Comma there. There's our graph, and you can see that it looks very similar to what we saw in Excel. But we like to do it in Python because this method is not subject to round-off error like Euler's method. Now we're ready to move on to Homework 1, Part A 2. This problem says 3 of the tanks in Part A1 are arranged in series, and the height of the liquid level in the third tank is to be controlled with a proportional controller that adjusts the flow into the first tank, i.e. Qn is equal to Qn naught plus Kc times H3 set point minus H3. Adjust the value of the controller gain to a value where the oscillations appear to neither grow nor die. This value of the controller gain is referred to as the ultimate gain, Kcu, that we would encounter in our later discussion of Ziegler-Summon's closed-loop tuning method. Set H3 set point to be 20% higher than the initial steady state of the third tank associated with an initial steady state inlet flow of Qn naught is equal to 0.1 meters cubed per second through the 3 tanks in series. So again, we are going to draw this scenario to better understand it. So the prompt says that we have 3 tanks all in series, where we have some flow in, and the outlet of tank 1 goes into tank 2, outlet of tank 2 goes into tank 3, and then there's a final outlet of tank 3. Each of these tanks has a liquid level. This would be H1, H2, and H3. Now, all these tanks are the same, which means that they all have the same cross-sectional area and the same outlet size. Each of these tanks can have their own differential equation to show how the height in that tank would be changing with time. So our first tank would be similar to what we were talking about in part 1. You would have your Q in minus A out the square root 2GH1. Now for the second tank, we know that our flow in is the same as the flow out of tank 1, AC PH2 dt would be A out times the square root of 2GH1 minus the actual outlet of tank 2, which would be this same thing, just with height 2. We'd repeat this same process for DH3 dt. So this time our inlet is the same as tank 2's outlet. We have our own outlet for tank 3. Another thing to note is this equation with our Qn equal to Qn naught plus Kc times H3 set point minus H3. Written out there. Our Kc is our controller gain, and then this here is our error, or E. Now what we can do is go on over to what we had typed up for part A1 and just make some adjustments to make this compatible for 3 tanks. So we already have our libraries imported and a lot of our parameters spelled out. Now we just need to add our Kc. We don't technically know the value, so we're just going to put a 1 for now. We were also given a new parameter, the set point, so HSP is going to be equal to 1.2 times our H naught, and this is representing that 20% increase from the original set point. And now what we want to do is define a function that's going to solve for the right-hand side of each of those differential equations. We can define it as right-hand side 3 tank. And so our independent variable is still time, but this time we have a vector. For our dependent variable, which we're going to unpack, so we have h1, h2, and h3 vector. Then we're going to define our error, which, as we just talked about, is just r set point, and then minus h3. And we can also define q in, since we were given that equation. This is in naught plus k c times e. And we're also going to define each of our outlets, so q1 out, q2 out, and q3 out. And what we can do is just go steal this section of our previously written code, and now we just need to make this 3 times, and we have to put that it's h1, h2, and h3 now. And now we want to return that right hand side, so that is our q in minus q1 out over AC for tank 1. For tank 2, remember that q1 out is the inlet of tank 2, so q1 out minus q2 out over AC. Same thing for tank 3, the inlet is the outlet of tank 2, out over AC. Work, and I'm just going to get rid of this because we don't need it anymore. Now, our result, we have to change this function name to our new function, which is right-hand side 3 tank. We still have these parameters set the same. This initial value is still good, but we want to have the same one for each of our tanks. Now, for plotting, our x-axis is the same, but now we have 3 tanks that we want to see on our y-axis, so we can have h1 plot, h2 plot, and h3 plot. Get rid of that. Now we have enter. Now same thing, we have scatter plots, but we want 3 of them, not just 1. Add 2 more. Change these to h1 plot, h2 plot, and h3 plot. Should run. Perfect. So it doesn't really look like much yet, but remember we didn't know what our KC was, and our goal is to find an oscillation that's not growing or dying out. So it's at 1 right now, so we could change that to 10 and see what happens. See, we're seeing more oscillations, but we're not quite there yet. We can do 20. So they're still growing. We need more. We can try 30. Now see, now they are growing, but just a little bit, so maybe we can go back down to 25. They're dying out. They're dying out. That needs to be bigger. 27. We're getting closer. Maybe 29. Yes, there we go. The oscillations are all even, so they're not growing or dying out.